This is part 7 of Programmer PIC Game, and it's about reading the switches. So the constants which have been added in this particular part are all to do with timing. So in this part, I add the final parts of the interrupts, the code for the interrupts, and most of that is to do with timing of the game. So I define 3 pause periods. So when I'm doing the game, there's 3 different lengths of time I want to show things to the user for. And in the interrupt, I scale, so we add interrupt for timer 0 and we scale it to roughly tenths of a second. It's not exactly tenths of a second, but just to get a rough idea. And then we scale that to a game period, which is roughly half a second. In the timer 0, we also do a sleep timeout to see if the device should go into low power mode. Player timeout, so when in the game, if the player is playing and he doesn't press a button for a long period of time, then he times out and he forfeits the game. And then add in one flag as well, which is the player timeout flag. So when the player times out, it will set a flag so the rest of the application knows that the player is timed out. So the RAM registers which have been added are very similar to the constants which have been defined, because they all are counters for the values which were defined in the constants. So this 10th one counts down for timer 0 what would be roughly a tenth of a second. Then the game counts down roughly half a second for gameplay interval, and the pause count counts for however long the pause period is supposed to be. The sleep timeout counts until no activities have happened for a certain period of time, then it goes to sleep. And the player timeout times out the game if the player doesn't press a button within a certain period. The only other couple of things which have been added in the RAM registers, which aren't actually going to be used in this part, but because they actually are used in some of the functions in this part, described in this part, is the level and the simultaneous level as well. But like I say, they won't actually be described as such in this part, but they will come along a bit later. So the first part of the coding is the actual interrupts. And the first interrupt is this interrupt here. And it's an interrupt for when an input is triggered. So when someone presses a button, and it's used for waking up the device. And as you can see, it's only 3 lines of code and it doesn't actually do anything. It checks to see if the interrupt triggered. If it didn't trigger, it just goes on to the next interrupt routine. But if it did trigger, all it does is clear the interrupt flag. But the reason why this is important to have is you need, if you get an interrupt trigger flag, you need to clear it. And the interrupt on the key press is just to wake up the device. And so when this interrupt occurs, it'll actually wake the device from a sleep opcode, and that's how that particular thing works. So the other interrupt handler which has been added is for timer 0, and that actually completes. This will actually complete the code for the interrupts, and there won't be any more coding for the interrupts. The only thing that will happen in further parts is a couple of lines will be uncommented. So this make rand is to do with random number generation, and that will be uncommented at some point. And these 2 lines down here where it sets the mode to sleep mode. Well, I'm not setting the modes currently, but that will be uncommented at a later point when handling sleep mode. But apart from that, the timer 0 code checks to see if the timer is triggered. If it has, it will pre-scale the timer to roughly tenths of a second here. And if the count hasn't got down to 0 yet, it will go to skip the interrupt and go here, where it just clears the interrupt flag. But if it has, it sets the count back up to tenths of a second. So next time it comes into this interrupt, it'll start timing the next tenth of a second. But after the tenth of a second, these functions here are basically the ones which have been in the test harness for previous parts, but now they've got a place to live, so they've been moved into the timer, this timer. And that's playing the beep. So in the previous part where we covered sound, this was in the test harness. Read keys, well, this is for this particular part because we're doing the reading of the switch values, so that's been added for here. LED display was in the previous part when we were handling LED displaying. and like I said earlier, make random in a later part for making random numbers. So another thing which has been added, so in previous test harnesses, I've just had like a count to do pauses, and it's just counted like 65,000 values, 65,000 loops, just to slow things down to show things in the test harness. But now actually the pause has been implemented in this part. And so here it's just checking to see if the pause is active. If it's not active, then we don't care, and we just skip to the next bit of code. But if it is, it decrements the pause count. And when that gets down to 0, it clears the pause flag. So the way the pause works is it's a multi-threading kind of way, in that in a part of the program, if you want to pause, you set a value, set this flag, and then when the pause is over, because the timer runs in the background, this pause flag will be cleared. So actually you can be getting on with other stuff whilst the pause is active, and monitoring for when the pause is cleared, and then continue with the program as it was before it was paused. So this next part of this timer interrupt is to do with timing of the actual gameplay. So it will prescale it to about roughly half a second, and then it does what it did for this particular timer, prescaling to like a tenth of a second. It sets the counter back to be scaled again for the next half a second. But after it's triggered, it checks if the pause flag is active. So this is what part of the program which is actually active on whether the pause flag is set or not. If the pause flag is set, then it just goes to the non-game apps, and it performs non-game apps down here. But within here, anything, this is to do with what happens in the game. Check to see if the player's timeout is expired, because if there's a player timeout, then it means it's the player's turn. We can do player turn code here, and it does that by this move flag opcode, moving this register just back into itself. So it really doesn't do anything. All it does is sets the value of the register to what the register value was, which doesn't do anything. But what it does do is it sets the 0 flag. So if that value player timeout count was 0, then the 0 flag would be set. But if it isn't the player's turn, then it goes on to the non-game opcodes again, non-game code. But if the flag, if it is the user's turn, then it decrements the timeout count for the user. So we can detect if it's the user's turn, they've taken too long, then we can set the flag here to say that the player has actually timed out their go, and they've forfeited the game. So now we're down into non-game operations. So this happens each time. So there's a sleep timeout, and so if the user hasn't done anything, whether they're in a game or not, for a period of time, they're going to low power sleep mode. And so if we're not going into sleep mode, it just goes down to here. But if we are going into sleep mode, then what it does is it just sets the mode to sleep mode. But we're not actually handling modes on this. This part of the code is commented out, but it'll be handled later on. And then so if it doesn't sleep, it does the LED animation, which is in the test harness from previous parts, and that's all that's added for this timer, and that completes all the code for the interrupts. We're just going to, like I say, uncomment some parts of this, couple of parts of this in the future parts. So moving on, the hardware initialization. There's just a couple of things which have changed in here. This interrupt on change. So if a GPIO input has a changed state, then it will generate the input. So this is for waking up the device if someone presses a button when it's in sleep mode. So adding that there. And then there's GPI, so interrupt on enable we've added as well. Interrupt on event happening to input, and also interrupt on timer 0. We've added that there as well. And then up here on the option reg, just one other thing, we just set a prescale for the timer 0. So in the actual test harness itself, as I say, most of this has actually moved into timer 0 now. So stuff that's moved out of here, things like displaying the LEDs, reading the keys, animating the LEDs. All this stuff now will be occurring automatically about roughly every 1/10 of a second, whereas before it was just in this infinite loop, which was occurring just as soon as it could get executed. But now it'll roughly occur every about 1/10 of a second. So this code itself, the test harness, has changed a bit. So as before, make sure the sound is switched on for the demonstration. And it sets the animation that we want as well, rotating the LEDs clockwise. But now it checks this key pressed flag, so a key press register. So automatically, when it reads the keys in the timer 0, it'll just update this register with anything it sees that a key's been pressed. And it'll add to it. So once a key's been flagged as pressed, that stays as flagged as pressed until it's been processed by the application, wherever, then that bit of the application will clear it so it can see new key presses. So it checks to see if any keys have been pressed, and like I've just described, it's moving the register key press to itself to check to see if it's 0. So if it's 0, then nothing's been pressed. But if it's not 0, then it will come down to this bit of the code, and it will set the tune to be played, and it will start playing the wind sequence tune. So it will animate the LEDs always, but when a key's pressed, it will start playing the wind tune. And then after it's handled that key press, it clears all key presses, so that next time it comes around the loop, so it goes around the loop after that, it can check to see if there's any new key presses, but only new key presses. So if I didn't clear the key press flag down here, it would just keep triggering, because it would never be, the key presses would just stay there. So you have to remember to clear the key presses after you've processed them. But that's the test harness for this part, and it's probably a bit more simple because most of it's been moved out into the places where it should be in the application. And the reset app function, this now is also code complete as well. Apart from, there's a couple of lines commented out here, again setting the mode of the game, which will be handled in a later part. But the bits that have been added are basically setting up the counters to be initial values, so that they're not some strange value when the program starts up or when the game resets. And it just, but it's clearing those. It's either setting the timer counts to their initial prescale values, or it's clearing the counts so that they're not currently active. So now come to the actual key reading functions themselves. So this is the main one, which is called in the interrupt, and it just reads the inputs of the device and updates the key pressed or key press register in RAM. Firstly, it checks to see if the application is paused, because if the application is paused, then the easiest way to pause the application is not to ignore anything that the user does. And that's also a good thing to do as well, because you don't want it recording key presses when it's paused, and then it comes out of pause and suddenly it plays back all these keys which were pressed whilst it was paused. That will have an unusual effect. So if it's paused, it just goes down to no keys, the end of the function, and doesn't do anything. It sets up just the values for the inputs of the GPIO inputs which it wants to read. And because the ports are being used as input and bidirectional ports, it's best just to set the value of the port to something you know before actually using it as an input, just so that it's a consistent state. And then I set the ports all to inputs for the switches, that is just the switches. And I put weak pull-ups on the ports, so they're pulled up to 5 volts with weak pull-ups. I read the actual state of the port, and I use an exclusive OR to invert the port state. So if you exclusive OR a value with all ones, then it actually inverts the bits. And I do that because the actual circuit pulls the ports up to 5 volts, and when you press the button, it pulls it down to 0. So key press is pulling it down to 0. Well, actually, it's more logical in software to read as key press as a 1. So I invert the value that I read. I mask out all the other values of the ports which I've read, and only have the key presses so that I can't get any spurious values coming in. And I add those values to the key presses, the key press registers. So if previously there's been key presses, then the key press register will have those in already. But I'm using an OR, so this will just add any additional key presses on additional switches into that register. Then I do a check to see if any keys have been pressed, because I use that to check if there's any inactivity for the sleep timeout. So when a key has been pressed, if I reset the sleep timeout every time a key's been pressed, then that value of the sleep timeout will only time out when there's been no key presses for the entire period of a sleep timeout. So this is the inactivity check to see if you should go to sleep or not. And then, like I discussed earlier, in the actual interrupt for timer 0 is when we check this to see if we should go to sleep mode or not. So that's actually the handling of key presses, but there's a few additional functions which I've got, which are to do with they're kind of helper functions. So wait until a key is down. So this function waits for the user to make a move in an actual game. So when it's played out the sequence and it wants the user to play the sequence back to it, between each of the player's key presses, it needs to wait for them, so that because it's got nothing else to do otherwise, meanwhile. So when it comes into this, it clears the current key press flags, because if it didn't clear the current ones and you come in here, and it will just drop straight back out because it'll think that the user's pressed the key. It also checks to see if the player's timed out, because if we're in here waiting for the player to press a key and he's not pressing the key, it will just wait here forever and never time out the player. So if the player times out, then it will return from here and it'll be able to tell the player that they've lost the game. And the other thing it does is it just reads the key presses which have occurred. So the time is still active and it's still reading keys, and it just checks to see when the players press the key, and when they have, it will come out of the loop. But if they haven't, it will just keep going back up the key loop and check to see if the player's timed out, and check for key presses, and it will just wait there until the player presses a key. And this next function is very similar. So the previous one was wait for a key to be pressed. This one's wait for a key to be released. And the reason we've got this function here as well is that in gameplay, one of the things in gameplay you can have is you can set the number of concurrent LEDs which can be on at any one time. So one of the sequences may be 2 LEDs or 3 LEDs or 4 LEDs being lit. And so I want to wait until all of the keys have been released, because humans aren't like exact and they're not going to press all the keys together at the same time. So what happens is once they've pressed one key, they then get a chance to, whilst they're holding that key down, to press all the other keys which that sequence can be made up of. So maybe 2, 3 or 4 LEDs. It's only when they release all the keys that it can then decide whether or not the keys that were pressed were correct for that sequence. So in this function, I'm going to use a new register called key log to log which keys have been pressed whilst we're waiting for all keys to be released. And I'm just going to keep adding any key presses which are which are registered into the log, and I'll clear the keys being pressed so that next time I add it to a log, it will just be new keys which are being added to the log. And whilst I'm doing this, because it's during the playback, I'm going to be beeping the frequency for the appropriate key. But if the simultaneous mode is actually beep for more than one LED key being pressed, then that makes a bit of a racket when you're pressing keys at different sequences at different times. So if it's a simultaneous mode where there's more than one LED being lit, then I'm going to use this register temp1, which isn't obvious in this code actually, but where this is called from, when the player is playing back, temp1 will be the frequency that actually is the target frequency, the actual frequency of the sequence is supposed to be, just to make it clean for the sound if it's in a simultaneous mode. But if it's not in a simultaneous mode, then we'll find out which key is being pressed. I'm just going through and checking the key log of which key's been pressed for the actual key which has been pressed, and I'm adding that to the W register. So at the end of that, I'll find out which keys are currently being pressed, and I make an offset into the frequency table of the key plus the frequency, this offset into the frequency table, and this offset is to make the beep higher than the lowest beep, so the frequency table, so it goes from low beep to high beep, just to shift the frequency up a bit. And I'm going to make the period of the beep as short as possible, so it's going to be a period of 1 for the beep, and I'll make the beep sound, and that'll go on in the background because that happens in the interrupts of the timers for actually playing the beep. I also check for player timeout, just like in the key down thing. When we're waiting for keys to be released, if the key doesn't get released, then the player could be timing out. And it's at the point where the player times out is when I want to tell them they've lost the game. So we check for that, and we'll exit this function if the player times out. So waiting for the keys to be released, we'll read what keys have been pressed currently. We use the trick of moving the register to itself to see if it's 0, if all keys have been released. If it has, then it will just come out and return. But if it hasn't, it'll just keep going around this loop until all keys have been released. And at the end of that, you'll have in the key log the actual value of the keys which were pressed during this period when we're waiting for the keys to be released. And then the final keys function is wait for no keys. So this is very similar to the first keys function where you're waiting for all keys to be released, and that's what this does exactly the same. But this happens when we go into sleep mode. So when it decides to go into sleep mode, what it does is it will wait for all the keys to be released before it actually decides to go into sleep mode. Because if it doesn't, and the keys still being pressed by the user, when the user releases the key, it will wake the device up again. So we want to make sure that the user's not pressing any keys and just keeping them held down when we go into sleep mode, or any other input for that matter. And I would just read the port directly this time, so I don't use the actual keys function. And I invert it and mask out just the switches. I check to see if any keys are being pressed, and if they are, then it just keeps going around this loop until all keys have been released. I make sure that the key press register is clear as well, because before going to sleep, don't want any keys to be registered as being pressed, because when it wakes up, it'll just try and process those, and they won't make any sense if it wakes up sort of when you use the device tomorrow and suddenly it's doing stuff which was logged from like the day before. So that's just a simple function which is called just before going to sleep, just to make sure everything is in a state where it should be before we go to sleep. And finally, for this part, is just the pause function. So the pause function in previous parts was part of the test harness because it was just like a temporary way of pausing until I came to add the final timer 0 interrupt. But now there's a pause function which you get called, and when you call it, you have in the W register how long the period is that you want to pause for, and it sets that into the pause count. Then it sets the pause flag to be set, so something can monitor the pause flag and decide when it's finished, because it will get cleared after the pause is finished. And in fact, we do that in this function as well. So this function won't return until the pause flag has been cleared. So that's timer 1. So we're just sitting here in an infinite loop until the actual pause is finished. But meanwhile, timers can happen. But as you saw in timer 0, it monitors this flag as well to decide when it's being paused, whether to do certain things or not. But it'll keep going around this pause loop until the pause is finished, and then it'll return control to the application. I've written the code to this PIC device, so if I plug the device into the circuit, the animation works for the LEDs, and when I press any of the buttons, it plays the sound.